Welcome everyone. Today we are very happy to have Huang from National Taiwan University, and he is going to tell us about classical spacetime from on-shell amplitudes.
Okay.
Over to you, Yuthin.
All right. Okay. Thank you very much for the invitation. Yeah, it would be really nice to have a visit. I hope that will happen sometime soon in the future. I really liked my visit last time. Yeah. So the topic of my talk will be on the classical spacetime from on-shell amplitude. It's going to be based on these mostly based on these four papers that we've put out since the past year. The past 2 years. And these are the collaborators. So I mean, so in the talk, when I refer to these paper, I just refer to these 1, 2, 3, 4. So, so how do I cannot, sorry, let me see how this, I have to do the navigator thing. Right, okay, so usually when we talk about black holes, we all often invoke the no-hair theorem, where we say that the black hole is characterized by just a few quantum numbers, so the mass, the charge, and the spin, and with no reference to its makeup. Now, of course, it's easy to notice that mass, charge, and spin is basically the same quantum numbers that we would use to label elementary particles. So we might ask that, so in which sense can we actually approximate a black hole as an elementary particle? And there's actually application-wise motivation for doing this, because as we know that for when we talk about black hole mergers, when we compute the gravitational waveform, and actually the whole merger process goes through 3 stages: the in-spiral, the merger, and the ring down. Whereas usually in the in-spiral phase, the black holes are really far apart, and therefore, in a sense, we can this process is described by viewing them as particles, as point-like objects. Now, of course, then you might say, but isn't everything point-like at large distances? So how do you distinguish something that is point-like at large distances, distinguishing something between a black hole and neutron stars? Well, actually, this is so. If we talk about things that are point-like, we usually what we do is we involve the world line formalism. Let me just put this away. Sorry. We use the world line formalism, and this is the usual world line formalism that we have in for example, quantum mechanics. But actually, we can actually include more and more so-called higher dimension operators, which describe how the world line particle couples to the background. So for example, at leading order, you will have a Riemann tensor square operator for a scalar particle, where E and B is the electric and the magnetic part of the Riemann tensor. And these actually encode what is known as a tidal Love number, which, for example, for black holes, these are 0, and they're non-zero for neutron stars. So you see that that actually using this world line effective action, you can distinguish between different gravitational objects. And if we actually include the spin degrees of freedom, so when this object has spin, you need to introduce a new degrees of freedom, which are these spin tensors here on the world line. And once you introduce this, you have infinite number of operators that you can introduce now, even just at the leading order. So this is just linear and E and B, and you have an infinite number of operators that can contribute to the world line action. So for each of these operators, you have a Wilson coefficient. And these Wilson coefficient then basically describe how this is a way of characterizing this spinning object. So for example, to compute the Wilson coefficients, so for example, if we're looking at a spinning black hole.
Sorry.
Yes?
I came in late. What is d mu, please?
Oh, sorry. The d mu is the covariant derivative on the world line.
Okay, thank you.
Yeah. So, right, so just as a simple example, let's say we have a rotating black hole, then we can take the linearized metric. So this is the Kerr metric. You just expand it to linear order. Linear order means linear order in for example, in G Newton. Then you have this linearized metric. The linearized metric sources, you can then invert this equation to get the source of the stress tensor. then this stress tensor becomes the Worldline operator that comes back and source this metric. So you can do this computation, and this was actually only done, I think, to all orders and spin more recently, and then you can compute these Wilson coefficient with these normalization factors for the Worldline operator. So for a Kerr black hole, in these normalization, all the Wilson coefficient are just simply 1. And yeah, so this Wilson coefficient being 1 will be the smoking gun for the presence of a rotating black hole, if we use this Worldline formalism to describe the point-like object.
And sorry,
yes.
sorry to interrupt you, Yutin, but you
No.
said these were the leading operators. So I imagine what you're doing is an expansion in the amplitude h mu nu, is it? So these are linear terms, and then you have quadratic and so on.
Yes, exactly. So these are so as you see, this is only linear in E and B.
Yeah.
So the quadratic term will be the as I mentioned before, the spin dependent love numbers. So E square and B square, which has the tidal deformations.
Yeah.
Yeah.
Okay.
So this is the leading contribution for now.
Right. Okay.
But you can suppose we had a particle orbiting in a black hole background.
Right.
Then these d mu's, wouldn't they be set effectively by the curvatures? So wouldn't these higher terms be effectively higher and higher order?
You mean that there's going to be a mixture between the contribution coming from these d's and then the quadratic and the Riemann tensor terms?
No, I just meant that if we evaluated, I'm thinking of d mu as a sort of like acceleration. Is that
right? They're related to the momentum. Yeah. Well, right. I mean, yeah.
So the acceleration would be set by the curvatures in some geodesic motion.
Right, but usually what we do is we do linear approximation. So the velocities, these are all, we're going to do straight line approximations. So leading order. So all of these computations are expansion in G.
So these d mu's are non-zero even for straight line motion.
Yeah.
They're not like accelerations. Okay, thank you. Yes.
Yeah. Actually, we'll talk about these computations in a few bit.
Yeah. Sorry, I missed what was E and B.
E and B is the Riemann tensor. So sorry. So let me go back. Yeah, E and B is like this. So E is the
okay. Thank you.
Yeah, but B is because there's a Levi-Chavita, so it's like a magnetic field, the magnetic component.
Okay.
Yeah. Great. Okay. So we see that we have a clear, even at linear order, we have a clear statement about what is a black hole and what is not a black hole, even though we're very far away and we're not talking about anything about. Is there a question?
Yes, sorry to interrupt you. Yeah. For just an ordinary straight, this d mu, what is it acting? Would it be zero if E and B was zero? Is d mu of S mu nu zero or non-zero in just pure straight line motion?
If there's no background, then this is zero.
This is just zero.
Yeah.
So the D acts on the E or also on the S's.
Yeah, actually, I'm sorry. So in our process, the D's acts on the E. So the D's will be carried and when we do the Fourier transform, it carries the whatever the momentum the E and B has.
I see. So these are like effectively like derivatives of the curvature.
Yes.
So why aren't they? I see. So it's just as Sandeep said, this is amplitude expansion, but not a derivative expansion.
Right.
Right.
Thank you.
Right. That's actually.
So this is like So this is exactly. So this as you see that this carries multiple moments in here. So it's multiple moments coupled linearly to the background, and so this would be like modifications for the 3-point amplitude, which is basically what the story of this whole talk is about the 3-point amplitude. And for the higher expansion term, the higher order terms corresponds to like 4-point Compton amplitude corrections.
Right. And sorry, after Shiraz, I have a question if you don't know.
Sure.
I'm done, Sandeep, sorry.
Okay. No, and again, I'm sorry, I might be anticipating what you're going to say, but just to ask you, so this is already interesting. You say, look, we can distinguish a black hole then from a neutron star, but just to understand it, are you saying physically the following? If you were very far from both objects, then of course, there would be a universal metric, which would be characterized by mass and spin, and if charge, then charge. But the difference between them could be told if you were to scatter a gravity wave of them, because then there would be a linearized, say, perturbation with which they would couple for the metric, and that coupling would be different in the two cases.
Yeah, at least in the current case, the spin coupling will be different for the two cases.
Will be different. Okay.
Yes.
Okay.
Yes.
Thank you. Thank you.
Sure.
Please go
Yeah.
ahead.
So, I mean, in a sense, it's a reflection of that, the fact that there's in principle that there's, of course, whether or not these all of these moments are measurable experimentally is another question. But in principle, you have infinite number of these moments. And for black holes, these infinite number of these moments are controlled by just a single few parameters. Whereas for a neutron star, then you have the equation of states, various things that modifies these parameters.
I see. Okay.
Yeah.
And could you give us a sort of physical sense for these parameters? Like, is it like it's not for is it like a dipole moment or something like that of the black hole?
Yeah, this is the multiple moment. But since you have a classical spin, so as we'll talk later on, so essentially you have an infinite spin, and therefore you have an infinite number of these moments you can compute. And how they enter, so for example, later on we'll explicitly compute, for example, the econol phase of the scattering event, and we'll see how these parameters enter.
So these guys are trivially zero for Schwarzschild black holes.
Yeah, they're zero for sure. There's no. Yeah.
Thank you.
Yeah. So this is a spinning object, right? Okay, great. So right. So we see that that it seems that C is 1 is the of course, I mean, you can explicitly compute it, and C equals 1 corresponds to black hole. But then we would like to ask, why is C equals 1? What is special about C equals 1? So the question we like to ask in this talk is, what is the on-shell statement of that null here theorem? What is really the statement that tells us that C has to be 1?
Hello?
Yes?
Yeah, you did. So if I may ask, so has this analysis that you described in the last slide been generalized to the case of charged black holes?
Yes, yes. So for charged black hole, then you will have another additional operator which couples to the background electromagnetic field. And then you also have these infinite number of moments for those.
Okay. And who has done it, if you roughly?
So for, I mean, the computation that is done in this kind of fashion, we actually did it. So we had a paper on Kerr-Newman black hole.
Okay.
And we compute these moments, and yeah.
Okay, thanks.
But again, for plain Newman black holes, just without Kerr, without rotation, everything would be trivial?
Yeah, I mean, there's no spin moments.
Right.
Right, so really what we care about is these A-dependent part, the A, which is a spin vector.
Right, right. And one more question, are things qualitatively the same in every dimension? Is 4 dimensions special?
Oh, we're going to heavily focus on 4 dimensions. So I think that there's some work that I know that are done in process and that are trying to do 5 dimensions and higher, where of course we have these Saturn, these black ring solutions. Yeah, so this really comes back to the question of in which sense that black hole solutions are unique. And in 4 dimension, the 4 dimension, the uniqueness is reflected in the usual 4 dimension spinor helicity variables that we are going to use later on. But in higher dimensions, the spinor helicity variables do not give unique answer, and it seems to be related to that the black hole solutions are not unique.
Excellent, thank you.
Yeah. Right. So. Right, we would like to have an on-shell statement of what this null-Hare theorem actually means. And furthermore, we know that in 4 dimensions, there's really a lot of different black hole-like solutions. So as we already mentioned a few, and of course, there's like Taub-NUT space-time. And so how are they encoded in this kind of statement? And finally, of course, is there any new underlying physical principle that selects these solutions? So in order to answer these questions, what we like to is to translate what we just talked about before into the world of scattering amplitude, where everything is on shell. And indeed, you can do that because whenever you have this whirl line operator, you can always sandwich this with the asymptotic state. And so, for example, we were talking about the leading order, which is the leading order in G Newton, which means that you have leading order Riemann tensor. That corresponds to a scattering amplitude of arbitrary spinning particles coupled to a graviton. So we end up with a scattering amplitude. So we're going to switch from this picture to this picture first. So we're going to talk about the possible structures of a scattering amplitude involving an arbitrary mass spin S to a graviton. So we would like to ask, how do we characterize this amplitude?
So the massive spin S guy is the black hole in your situation.
Yes. So we're going to approximate that by this massive particle. Right. So we're going to use a formalism that was developed a couple of years back for massive scattering amplitude. So the basic idea is that we know that the scattering amplitude for massive particles, for the in and outside, if it involves massive particles, it should carry the SU2 massive little group. So we need to find objects that transform covariantly under these SU2 under the SU2 group, and therefore form representation for these SU2 irreducible representation. And just as the usual spinor helicity formalism, where we just take the momentum and we write it into a bispinor form, since the usual spinor helicity tells us that if something is massless, determinant of this is 0, and therefore P alpha alpha dot is a bispinor. You can write it as a bispinor because it's rank 1. For massive, that all that's changed is that now is no longer rank 1. Then that means that this bispinor is this bispinor 2x2 matrix is constructed from 2 spinners. And since you have 2 spinners, it's natural to organize it into a doublet. So these two spinners can be labeled as 1 and 2. And by reconstructing this as a doublet, that lets you manifest the SU2. So this doublet SU2 is exactly the massive SU2. So once you have these spinner, then these spinner then just becomes your so-called external line factor. So for example, if you have some amplitude that transform for particle 1 is in the S1 representation, spin S1, then that means you have 2 S1 SU2 indices that are totally symmetric. And since only these lambdas carry the SU2 and these SU2 indices of leg 1, that means that it must be proportional to these lambdas here. So these lambda, you have 2s1 of these lambda, and they're totally symmetrized. So these are just like the external line factor, except that now everything is written in terms of spinor, and everything is on shell. So there's no, you no longer need to introduce polarization tensors and then try to solve the longitudinal equations. Then you just write everything in terms of these lambdas ones. So since this is universal, so really this is not the point. The point is what remains here. And what remains is these, since these spinners also carries a space-time SL2C indices. So that means what remains is a symmetric SL2C tensor. So for example, if we have this 3-point amplitude of a massive particle at leg 3 and massive at leg 1 and 2, that means the tensor structure that you're interested in is some 2s1 and some 2s1 and 2s2 SL2C symmetric tensor that carries some H little group weight. So basically, you're trying to find all the possible tensor structures in this object here, and this object now only carries SL2C indices. So since you're looking at tensors in SL2C space, that means we only need 2 vectors to span that space. So so we're looking at for this object, and we need 2 vectors to span that space. And the natural, and of course we don't want to introduce anything auxiliary or any auxiliary vectors. So the natural thing to have is this actually the spinor associated with this massive leg. So let's introduce lambda 3 alpha being one of the vectors to span this space. And then of course, once you have this vector, you have the orthogonal vector here, lambda 3 orthogonal. So you can use these 2 vectors as U and V to basically to try to span this space. Now, as you can immediately see that this is not sufficient. I mean, of course, in terms of spanning the possible tensor structure, these 2 objects are sufficient. But you also know that it has to carry a particular little group weight for the leg 3. Now, lambda 3 already carries a little group, but it carries a definite little group weight, which is 1/2. It has in our convention, it will be, in our convention, it will be -1/2. So you need something to carry the opposite helicity weight. And the natural object that you'll find is that you notice that since you're talking about the same particle from the same state coming, or it's the same massive state coming from 1 to 2, that means M1 is equal to M2. That means we're talking about a degenerate kinematics. Since M1 is equal to M2, so P2 plus P3 squared is going to be equal to P1 squared. Since P3 squared is 0 and P1 squared is equal to P2 squared, that tells you that 2P2 dot P3 is actually 0. So when these masses are the same, the momentum inner product of the masses and the massive leg are just 0. What that translates into spinor language is that this lambda 3 here is actually proportional to the lambda 3 tilde times P2, because the contraction is 0. So that means lambda 3 alpha is proportional to P2 alpha alpha dot times lambda 3 alpha dot tilde. And therefore you define a proportionality factor here. So this is X. So this X, since this has -1/2 helicity and this is +1/2, so X carries the opposite helicity, which is +1. So at the end of the day, all of this analysis just tells you that if we think about this process in a completely on-shell fashion, then this process is just parameterized by 3 objects. First is this X, second is this lambda, and the third is of course, the Levi-Civita 2x2 tensor here. So these are the fundamental building blocks to span the possible tensor structure for this scattering amplitude.
So sorry, this is probably really dumb, but doesn't this amplitude vanish on shell if you go to the rest frame of the second particle, the massless particle has 0 energy?
Right. So this is what usually happens is that when you're trying to talk about 3-point amplitudes, I mean, usually you have, if we're in real kinematics, and everything is 0, and it vanishes. So in the sense that what we're really doing is we're doing to complex kinematics.
Oh, I see.
Yeah.
Okay.
So we're analytic continue to complex. Yes. I mean, this is also the same thing that happens in when they usually talk about massive scattering amplitude. The 3-particle phase space is 0.
Actually, I didn't understand that. Why can't a massive spin S particle decay into 2 gravitons?
No, it's the other way around, Shiraz. There are 2 massive particles and 1 massless.
Ah, 2 massive and 1 massive. Thank you.
Yeah, 2 massive and 1 massive. Yeah.
Okay,
And the mass are the same.
Yes.
Thank
Right.
you.
So, sure. So of course, so now the
I
yes.
missed some of your kinematics. So there's some variable telling you what the polarization of the massless particle is, and some variable telling you what the polarization of the massive particle is, right?
Right. So the rule is that if the massive particle is spin S, that tells you that you need 2s of these SL2C indices and 2s of the other SL2C indices for this to come out. So that's the rule reflecting that you have spin S massive. And then you also need to have the correct little group weight, which is carried by the lambda and the X. So they have to combine in such a way that it gives back the correct little group weight.
So lambda is giving me polarization information of the massive particle?
Of the massless.
Of the massless.
Yeah.
What is giving me the polarization information of the massive particle?
The 2s. So because this is symmetric 2s indices, so that tells you that the massive particle is a 2s represent as spin S.
So these are free indices. I see.
Yeah, these are free. These are totally symmetric free indices.
I see. So this is alphas for the initial, let's say the ingoing particle, and beta for the outgoing.
Yes. Yes. Okay, yeah. So and this will be immediate and transparent when we try to do an explicit example, which is here. So for example, we write down all the possible tensor structure. For example, for spin 1/2, that means you need an alpha and a beta. And so, for example, this is electric coupling. So for example, if you couple to +1/2 photon, then this is the 2 possible combinations that you can have. So it must have alpha 1 index and also have beta 1 index. And the total little group weight has to be +1. So lambda has -1/2. So that's why this has an X factor here. This M is just normalization. So everything has the same dimension. So as you can see that basically for spin S, you have a 2s + 1 tensor structures that is possible to write down. So this is just completely on-shell way of parameterizing the possible spin interaction with the object. And not surprisingly, because
sorry, you think I thought your object had two spin labels, right? S1 and S2.
Yeah, so because spin one
of
half,
one particle and the other particle.
right? So here alpha is the one particle and beta is the other particle. So
Okay.
so S1 is spin one half for that case, so you only have one index for one particle. Then S2 is also one half, so you also only have beta 1. So that's why for spin one half you only have one. But if spin 1 you have two, so you have alpha 1, alpha 2, and beta 1, beta 2.
No, but can you not have different values for spins?
Yeah, but we're looking at equal spins for the current for our purpose. Yeah.
Okay.
So we're looking at equal.
Okay.
Yeah. Yeah, and since we're defining things in a completely on-shelf fashion, so not surprisingly, all of these things actually have physical meaning. So for example, here, you can just use the usual textbook QED, the amplitude, and then you just plug in the spinor variables and do some algebra, and then you'll find that this collapsed back down to just EX 21. 21 is, remember there was external lambdas. So that means it's the external line factor 2 and external line factor 1 is contracted with the Levi-Civita, which is this set factor. So QED is just minimal coupling here. And this factor, not surprising, is just G minus 2. So this separation is just very clean. And right, and so for S equals 1, you have three structures. So this is the WW, the WW gamma, the interaction. And these are the anomalous moments that you have for spin 1. And you can continue this on for arbitrary spin. So even though we don't have a very clean Lagrangian approach to just talk directly about arbitrary massive higher spin, but at least there are 3-point couplings to massless particle that have this very nice kinematic definition about or this very nice kinematic parameterization for how any arbitrary higher spin particle can couple to a massless particle.
So there are two undetermined constants.
Right, so these are undetermined constant here. These G's that I write down are all undetermined. Okay, so from this point, this parameterization point of view.
Hello.
Yes.
So for S equal to 1 for spin 1.
Yes.
One of them is anomalous magnetic moment. What is the other?
I think a quadruple moment.
A quadruple moment.
Yeah.
You said. Okay. Thanks.
Sure. So right. So these are the general parameterization. Then from this point of view, if we look at the simplest possible scattering amplitude for for arbitrary spin particle coupled to a massless object, you would say that the simplest thing is just all of these G's turn off. As we have already seen that, so the simplest amplitude takes this form for arbitrary spin, which is just very simple. It's just X, nothing else, times these epsilon tensors. Or if I put back the external line factor, it looks like this. So we can ask what actually corresponds to this kind of interaction. Now, of course, as I already mentioned, that for spin 1 half and spin 1, this is just minimal coupling for QED and electroweak coupling. If you look at spin 2, for example, if you look at the massive KK graviton, this gives exactly this kind of coupling for S equals to 2. But what about S, arbitrary S? Is there something in nature that couples in this fashion for arbitrary, if we let S to be arbitrary? And since we already introduced in the beginning this world line operator, this world line formalism, we can match these two descriptions in terms of the on-shell world to the world line world. And if we do this by taking this amplitude and then we translate it back to the world line action and matches to the C, what we find is that for minimal coupling, the C, the particular these Wilson coefficients for S takes this form, and so for higher and higher S. So this means that if I take what we call the classical spin limit, which is taking S goes to infinity, but an H bar to 0 with S times H bar fixed, so that you have a classical spin, then all of these terms actually drops out. And this description about, so in other words, you take S to infinity here by keeping H bar fixed. This goes this collapses into the black hole coefficient, 1. And you can show that if you actually allow non-trivial G's here, then this will not occur. So only when you have no G factors and you only have this minimal coupling factor, and you take the classical limit of this coupling here, and you reproduce the black hole Wilson coefficient. In other words, so minimal coupling for higher spin actually yields the leading order spin multiple for a Kerr black hole. So this would be then the object in nature that actually couples. The Kerr black hole is the object in nature that actually couples through minimal coupling. And we can make this more precise by just computing physical observables. So for example, so once again, we have this minimal coupling 3-point interaction. So for example, we can compute the classical gravitational potential. And you can compute this from scattering amplitudes. So we can compute the leading G potential by consider you have some massive object here, and then you take and then you exchange one graviton, and you take where the transverse momentum goes to 0. So you take the t goes to 0 limit of this, which corresponds to you're looking at the large distance effect, and that corresponds to, if I translate into t into this q here, so that corresponds, you're taking to q squared go to 0, and this amplitude, of course, will then in that limit will factorize into the product of this 3-point. So this residue here is basically the product of the 3-point. So if the statement that this 3-point gives the Kerr black hole has any teeth, that means that if I plug this into this residue and do this transformation, and then Fourier transform to position space, I should match the GR prediction of the gravitational potential that you will get from computing via GR. And indeed, we'll find an exact match, and which matched to the Kerr black hole leading post. This is post Minkowskian because we're expanding in G. So this is how the potential looks like. And if you do this and then do Fourier transform, you'll match exactly with this potential. So good. So we've succeedingly in identifying that this minimal.
Did you check the black hole has all G's equal to 0 except for the first one?
Yes, that's basically the statement. So that's actually, so that's the remarkable thing here is that when you look at the world line, if you look at the world line point of view, then to describe the spin multiple at leading order in G, you need all of these Wilson coefficients, and everything is 1 for in this frame, in this Lagrangian frame formalism. But if I look at the on-shell formalism, then it's just a single object. So this on-shell object actually reproduces all the multiple moments. So that's basically the statement.
So you think when you parameterize this 3-point coupling, instead of, I mean, you have this G's, which are the couplings, but in front of each other, there could be some constant also, right? You are taking that to be 1. The first term,
right? So this is just normalization. So really, what's meaningful is the relative ratio between what was behind in the first term.
But I thought if you want to compare this with the Wilson coefficient, that's also just an overall factor.
Yeah.
For all C's.
Of course, that corresponds to how big G Newton is.
Okay. And also another question is that in string theory, the coupling in this language, does it take any special form between?
That's a very good question. So that's one of the things we're analyzing. So in other words, we're looking at the first of all, for string theory, there's something very interesting. So unfortunately I didn't put anything here about string theory. So in string theory, first of all of these G's are basically not 0 except for the G minus 2. So if we're looking at open string where you have massive, if you're looking at a 3-point amplitude in open string where you have 2 massive spin, you can be leading trajectory or subleading trajectory, and then coupled to a massless vector, the massless vector. The G minus 2 factor is 0, but everything else is not 0. So this is one interesting aspect of that. The other thing, of course, in principle, you should expect that because string is extended, so you should expect it to have all these non-zero moments. There's actually a very nice trivial understanding of why for string theory all the states are G minus 2. That the G minus 2 is actually, and the reason is because you know that open string double copies to gravity. It double copies to closed string at 3 point. And for closed string, there is no lambda object here, because the closed string you start with Riemann tensor, and Riemann tensor is a 2 derivative, so you cannot have this lambda. So if something double copies to a closed string, it cannot have this lambda piece in the open string sector. And that's a very simple way to see why for any, it doesn't matter if it's leading trajectory or subleading trajectory, the G-2, this G1 has to be 0 for all open string states.
But
thank you.
as you go to higher order, there are zillions of different string states with higher spin, with given spins. So there's probably no universality, right? Different states behave differently, presumably.
But for all of those string states, they all individually double copy to gravity. So for example, so this is an argument that all the string, and doesn't matter which order, subleading trajectory, they all should have vanishing G-2. And we've checked this up to level 8. So we're actually interested in this, and so we're doing the computation. So we checked to level 8, where level 8, for example, has degeneracy 2 for spin 4 and degenerate 4 for spin 2. So all of these things all have 0 G-2.
Right. No, but even at the level of closed strings, there are plenty of higher spin closed strings.
Right.
So if you've got something that's 0 for every closed string, great, that will be universal. But if something's non-zero, the non-zero values would not have any universality you would expect, right?
Yeah, non-zero would not. Yeah, so one of the things that might, yes, exactly. We're not saying there's any universality. We're just studying the pattern, because we were thinking that there might be some interesting, because once the degeneracy, whether or not when you start to look at really subleading trajectories and where the degeneracy starts to pile up, somehow these closed string states start to become black hole-like. And maybe these higher moments will start to be suppressed.
And sorry, Yutin, one more. Suppose you wanted to start probing the Kerr black hole to nonlinear order.
Right.
Then you would have to look at the 4-point function, for instance, of this.
Yes.
2 gravitons.
Yes.
But in a black hole, you don't expect there to be new information there, right? Somehow
yes, that's the fascinating thing. So this also motivates. So we're really sorry, we're really jumping ahead. But so we see that we have a unique choice for 3-point coupling in terms of looking at this. But once we go to 4-point coupling, where you have 2 gravitons, there's really not a unique choice for what is the correct, as I would say, the Compton amplitude for these higher spins. But black hole should give us one unique answer. And it's actually curious that so right now the gravitational community, so in order to be sensitive to that those quantities, you need to go to 2 p.m. and high spin. So this needs to go to 2 p.m. and spin vector to be degree 4 and higher to be sensitive. And they only compute up to now degree 3 in spin vector. And so even the GR community has not computed to the level in which we have that information yet. But yes, I agree that there should be, the black hole has a unique answer, but from this on-shell point of view, the on-shell point of view, the 4 particle does not have a unique answer. And so there seems to be a mismatch there. And yeah, so it'll be interesting once if the gravitational community can compute that object, and then we can come back and look at what was special about the choice that was picked out by the black hole. But right now we don't have an understanding. And that's one of the reasons that we started to look beyond, which I will talk about later from the entanglement point of view.
Thank you.
What principle might there be? What further principles might there be? Yeah. Okay, so the fact, so what is actually this fact that the minimal that the Kerr black hole corresponds to minimal coupling actually tells us about Kerr itself? So is there some lesson to be learned here?
Hi, can you hear me? Sorry.
Yes, indeed. Yeah.
Sorry. Just can you go back to your previous transparency? Just
this one.
Yeah. I just want to. There's something I'm not fully clear about. So this, what you've written down, V classical BBN, then is the scattering between 2 black holes mediated by a graviton, if I understand.
Right. So or more precisely, we're extracting the gravitational potential from the S matrix in this fashion.
Yeah. Okay, good. Thank you.
Sure.
But that is you write, I guess, T going to 0. So the momentum exchange, this is the momentum exchange going to 0 limit, is it? Or rather T going
or
to
null limit, or Q squared go to null limit.
Yeah, that's what I meant. Q squared going to 0 limit. Okay.
Yeah.
But there would be a systematic expansion in powers of Q.
Exactly. So we're taking the leading piece.
Right. But normally, for example, when we talk about the multiple pole moment expansion, that corresponds to higher and higher powers of Q square, right? In that you look at terms which fall faster and faster in 1/r, say the distance between the two particles.
Right. So there's also a Q in the spin vector. So usually it's expansion in Q dot S. So yes, there's more and Q factors there.
I see. And so you could in principle then sort of taking this forward, working still in the regime where you're looking at the linearized coupling of the massive particle to the massless one, you know, work out the systematic Q square expansion, I suppose.
You mean do further expansion in Q square?
Yeah, beyond the leading order here.
Yes.
Okay, and that will give you sort of the analog of the multipole expansion for this process, I imagine.
So there's the but because of course even without spin you can do the subleading Q square expansion, right?
Yeah.
So really usually what this is done is you have the Q square expansion, then the Q dot S expansion, where the Q dot S expansion is expanding in spin.
I see. And so in that sense, you can find out the multipole moments, so to say, for black holes. That would be responsible for their, you know, potential or scattering in general.
I think Sandeep got all orders in this Q dot S already.
Yeah, this is all order in Q.
This is all orders?
Yeah, because you can see that there's a cinch factor here. So the cinch is, these are all orders.
No, I'm sorry. I see. Where is the Q sitting in SA?
Oh, I mean, this is Fourier
transform. The grad.
Yeah.
Okay, but wouldn't there be still corrections in 1/Q square to this? You know, like in the multipole moment expansion, that is taking even the spin to 0 if you were looking at two non-spinning black holes.
But those, because we're Fourier transform to R space, so those will correspond to delta functions and stuff. And so those are not visible in the long range. So we're looking at long range effects. Of course, when black holes are close together, then they're now no longer point-like. So we need to take the long range approximation.
I see. But you couldn't repeat this to compute subleading. You should go on, but you can't use this to compute subleading in in Q square, subleading in Q square terms. The ones, for example, which might be the analog of the quadrupole, the ones which fall faster in R. Or am I missing something?
It's not just falling fast because you're doing the Fourier transform. So there's also the spin part that is. So in other words, the Q dot S, even though it's higher power in Q, it doesn't fall off that, and you can still measure it because there's a S. But if it's not just Q dot S, it's actually just Q squared, the subleading term, and those are just delta functions, and they're not relevant for long range physics.
Hi, maybe if I may comment, you know, like Sandeep, I think what is happening is that if you let many of the grads act on 1/R, you'll get the faster fall-offs that you're talking about. So,
I see. But what about the non-spinning case? Okay, I see. Okay, anyway, go on. Sorry, please go on.
No problem.
So, Yutin, sorry, a basic question.
Yes.
Yeah, in this, the way you compute potential, I mean, that would be result of multiple graviton exchanges, right? So is there some sort of an exponentiation going on?
Yeah, actually, so since we're taking, so of course, what really happens, so usually when you try to, so this is just getting the gravitational potential. For the physical effects, I usually do is you compute this first, so this is leading order in G, and then you compute this is the equinal phase, basically. And then you exponentiate the equinal phase. So that gives you the ladder the all
Right.
the three sum ladders. Yes.
And the non-linearities don't matter because we are just looking at leading order in G.
Yeah, this is just thinking. Yeah, so this is what is called 1 p.m. So this is just leading order, and the non-linear, the as we mentioned, like the Compton, where you have 2 gravitons coming out, those come in at 2 p.m. Those are
So
higher
PM
order.
stands for what?
Post-Minkowskian expansion. So that's you're expanding
Thank
in
you.
so you're expanding in post-Minkowskian. Sorry.
Thank you.
Okay. So right. So what?
Sorry to interrupt so much.
Yes.
Just to make sure, just in motivated by Sandeep's questions. In the Kerr black hole, if we look at we take the metric and expand it to leading order in 1 by r, there's a non-trivial function of theta behind that. Is that right?
So this is the linear metric where we expand to leading order.
Right.
So
Yeah, I was wondering, the higher functions of theta, do they come with an extra powers of 1 by r in the Kerr black hole metric? Or just in leading order 1 by r, there's a non-trivial function of theta? This may be a coordinate dependent question,
yeah.
but at least in the usual coordinates. My memory is that there's a non-trivial function of theta even at leading order. Is that wrong?
I think that's
yeah, it sounds right. Should I say what again the question is? The leading 1 over r, is that dependent on theta?
Yeah, is there a non-trivial function of theta behind that?
Yeah, I think so.
Yeah.
That's what I recall also.
That's what I thought. So then somehow this multipole intuition isn't quite working out, right?
but I think that the thing is related to yeah, let me just see if I have it here, because we have sorry,
I don't want to interrupt, but again,
yeah, I think theta is, oh sorry, I think that theta is this a cosine theta here, right? So you're saying, I mean, in this coordinate system you do have this, so the cosine theta is coming in with the a.
Right, so you get some non-trivial theta dependence. Maybe you won't call it non-trivial. Maybe. So I'm just wondering.
Yeah, so this expansion in a here is really an expansion in a cosine theta. So it depends on what coordinate system we're talking about.
Right, but higher and higher orders of this have higher and higher powers of 1 by r?
Sorry, let me just go back. So yeah, higher order of this, yes, because we have derivative acting on this r.
Good. Then I withdraw what I was asking. So then it's the usual multiple story.
Yeah. Yeah, so these derivatives gives you the higher powers of r.
Okay. Yeah, Loga, you were saying something, sorry?
No, I just wanted to say that, all these powers of r are completely determined by saying that these are tensor multipoles. Right? You're just doing tensor multiple expansion.
Right. Okay.
Yeah.
Okay.
Anyway.
Thank you.
Okay, sorry. Yeah, so right, so I wanted to talk a little bit about what actually can the fact that I match it to minimal coupling, this very fact, what does that actually come back and tell me about Kerr? And it actually tells us it gives us an interesting way of seeing some things that are discovered in the past. So we're saying that this minimal coupling here, if I take x, so the only difference between electric and gravitational is just that the x goes to x squared because of the fact that the photon gets another helicity when you square it to graviton. So actually the two are there's two things that are described by the same coupling. So that, first of all, that tells us that the Kerr, at least at linear order, supposedly, that the Kerr should be given actually as the square of some electromagnetic solution. And indeed, this was also shown a while ago that by Donald O'Connell and collaborators, where if you look at the Kerr-Shell form of the metric, so you can write the metric in the Kerr-Shell form where you just write the metric with the flat component piece and 2 null vectors times a scalar function. And if you just take the single copy of this, which means by single copy, that means that you take the one piece of this null vector and then using the same scalar function, then this will be a solution, for example, for linearized Yang Mills. And so in there, they showed that, for example, the short shell solution, if you do the single copy, gives back the Coulomb potential. And if you take the Kerr solution, which is rotating, you get a rotating disk. Oh, sorry, this is cut off with a radius, a fixed radius, which is related to the spin vector. So they found it in the Kerr shell form in the coordinate system here, but here we see that on the on-shell form, this is just automatically manifest this double copy relation. Furthermore, the fact that it's minimal coupling reflects the spin dependence is really completely intrinsic. And this actually gives an on-shell explanation of something that was discovered long ago by Newman and Janus. And so we can see immediately what I'm talking about. So remember, we have this 3-point amplitude here, which is minimal coupling. So why does this have any spin dependence? The reason is because, of course, that these 2 and 2 primes are different particles. So there's a Lorentz boost that relates the 2 to the 2 prime. So if you have 2 prime is related to 2 by Lorentz boost, you can work out explicitly what this Lorentz boost parameter is. And then once you plug it in, you can see that the 2 and 2 prime actually can be rewritten as, once you converted everything to 2 space, you can separate into 2 terms. First is the identity. You can view this as an identity in the little group space of 2. And then you have the spin rotation piece, where this is basically Q bar. Q bar is the wave number, and S is the Pauli-Lebensky spin vector. So that means if I write it in this form, then we can see immediately that the minimal coupling, when I write it in this form, or more precisely, I write it in this little group space form because its identity is in the little group space of 2. Then it takes this form here. And then I can just straightforward take the classical limit, which is to take the S goes to infinity limit. And then we see that this exponentiates. So this means that this minimal coupling in terms of the spin vectors, it actually exponentiates in the classical limit. So the spin factor actually exponentiates. So what does this exponentiation actually means? It means that whenever you're computing some physical observable, the difference between a non-spinning object that corresponds to minimal coupling, and a spinning object is this exponentiation factor. So for example, what does this mean? So let's say we want to compute the impulse. So the impulse would be so this is the massive object here, and let's then send in a scalar probe. So we want to compute the impulse that the scalar probe feels in the presence of this gravitational background, this object here. So that means that in the scattering amplitude event, you have this massive spinning object sourcing a graviton and affecting this scalar probe, and the scalar probe feels the impulse. So the precise formula for computing this impulse from the scattering amplitude is given here, where you have the 4.222 scattering, and then you weight it by Q mu, which is a transfer momentum, and you integrate it over Q. And then, but this, you need to take the Q squared go to 0 limit of this amplitude. The form of this amplitude, you need to plug in the Q squared goes to 0 limit. Of course, this can be easily justified just by thinking that you're averaging. I'm doing an average over the transverse momentum weighted by the amplitude. But you can derive this in a much more rigorous fashion in quantum field theory, which was done by O'Connell and David Kassower and collaborators last year. And so if I plug in, so once again, because I'm looking at this 4-point amplitude and the Q squared goes to 0 limit, that means that it factorizes into 2 3-point. And therefore, it's basically just the product of these 2 3-point amplitudes together. So there's 2 pieces here. One corresponds to the positive graviton exchange, but the positive helicity exchange. The other corresponds to negative helicity exchange. And so these are the 2 answers. These are the 2 contributions. And then you just do the Fourier transform. So of course we can match the final answer, but important point here I want to stress is that this tells you that the relation between a non-spinning object and a spinning object is this exponential factor. So what this exponentiation factor affects is that in this Fourier transform, it's going to shift this B by a complex value, which is proportional to the spin. So you're just going to shift the B, which is the impact parameter, by an IA. So in other words, you can, in terms of physical observable sense, if I'm considering some scattering event in the, for example, in a short shell black background, I can immediately get the Kerr result just by shifting the short shell solution by a complex shift. And this is a renowned discovery, the famous Janus-Newman shift, which was discovered long ago, right after Kerr solutions were wrote down, where they actually showed that if you write the black hole solution in Kirchhoff form, so once again, the Kirchhoff form is just that you write the metric in terms of, by the way, this is exact. So you write it in terms of a flat metric plus 2 null vectors times a scalar function. Then for Shortshot, it's simple. It's the scalar function is just R naught over R. But for Kerr, it also takes this nice form where now you have R squared plus A squared times cosine theta squared, where this cosine theta squared is what Shiraz was referring to earlier. And you can see that you can immediately get this solution from this solution just by shifting R to R plus I cosine theta. So you write this as a sum of complex conjugates so that this is real, and then you do this shift, you immediately get the Kerr solution. So this Janus-Newman shift generates, this shift takes you from the Shortshot solution to the Kerr solution. Now this, of course, you can say that this shift is, well, this is mysterious, of course, because it's not guaranteed that you do this shift for any arbitrary solution of Einstein equation, you get another solution. Furthermore, it'll appear that this is actually coordinate dependent. But in our way of showing things is that you actually immediately see where the shift is coming from. It's coming from, well, whenever you have spin, when the spin is describing what is generated from black hole, it exponentiates trivially. And once it exponentiates it, then that means that the difference between a spinning black hole and a non-spinning black hole, there's this exponentiation factor which induces on the physical observable this complex shift in the impact parameter space. And this is precisely the Janus-Newman shift.
So is there an equivalent of this shift in higher dimensions?
I'm not sure. Sorry, I haven't. Of course, their shift was for 4 dimension. I don't know if there's something similar in higher dimension. Sorry. Okay, so we see that minimal coupling can actually include.
Sorry, Eugene, can I ask a question? So
sure.
how do you go from this complex phase shift in the scattering amplitude to this shift in this phi?
So of course,
yeah.
as well also, of course, because we're computing a physical observable. So actually, there's a more straightforward way. There's a straightforward way to see this because you can compute this impulse by using the geodesic equations. So you can see that if you do the impulse, so this is an amplitude way of computing the impulse. But you can also use the geodesic equation to do the impulse computation. And when you try to do the geodesic equation, when in that computation, the two solution, you do this Janus-Newman shift on the gravitational solution, and then you can match these two computations at an equation level to match it with precisely this extra shift that you have from the amplitude. But in this sense, so you have to go through the physical observable.
And that is a complex shift even at the end answer. Is that the statement? So you
Yes,
started with a phase shift in the scattering amplitude.
Right.
The statement is that if you take it and match it against the geodesic, it's still a complex shift on the geometry.
On the impact parameter when you after you finish, right? So because we're talking about physical observable, so I'm saying that if you do this shift on your geometry, so if you do this Janus-Newman shift on your geometry and then you plug it into the geodesic equation, the effect of this shift is also will be reflected in this shift in the impact parameter in the end of the computation.
Okay, one more question. So you had this effective potential that you showed. So is there a way of going from this shift and thinking about the effective potential also as having a complex shift?
That's a good question. Let me think. I know that the original, the way that the potential derived was not through this shift. I don't know if there's a way to derive the potential. So the way that they derived the potential, actually, the way that actually that closed form for the potential was derived was actually going through the world line computation. So they computed the world line once. So this is, you'll notice it's the same paper. So they first get the world line and get the Wilson coefficient. And then they take the two world line and sourcing this background to get this potential. So that was how the original computation was done. I would say that in hindsight now that you can see that you can actually do it just from the shift, because as we mentioned that this roll line coefficient C's, these coefficients are just generated by the minimal coupling, which is generated by the shift. And so in this roundabout way, I would say that you can get that potential from that shift.
For example, can I understand all these cosine hyperbolic operators that occur by just thinking of them as adding some two exponentials or something?
Yes, yes, basically that's how we derived it when we were matching to this. Yes.
Okay.
And Newton, does this way of going from Schwarzschild to Kerr persist at higher orders also then? I mean, because the Kerr-Schild form does allow you to relate the two solutions exactly.
Yeah, yeah. So that's something that we want to understand. And as I mentioned, because this is we're only talking about 3-point coupling. So we have to understand what this shift means when we include the higher point interactions.
Yeah.
Yeah. So that's part of the mystery about the higher points.
But it seems there should be some kind of a relation.
I agree. I agree.
Okay.
But if we just talk about amplitude, so I mean, but because 3-point here, there was something very simple about that minimal coupling. And which we can just, without thinking about black hole, we just select that minimal coupling. But then at 4-point, yeah, we haven't found the physical principle except for trying to do the shift and matching the results. But what is actually, yeah.
About that, you know, this kind of issue has come up recently in all these discussions of this Polyakov, the Polyakov block stuff. You know, if you try to construct some sort of canonical interaction involving the exchange of a certain particle, that becomes ambiguous because of the ambiguity of a contact term interaction.
Exactly. So these are the ambiguity with the contact terms. Yes.
Right. And a principle that has proved quite useful recently is to try to choose the contact term to make the Regge behavior of the 4-point scattering the softest possible. I'm wondering if the black hole will automatically do that.
But is that sufficient to uniquely fix the interaction term, the contact term?
Well, I think there are at least some claims that that's sort of sufficient, right? Abhijit knows this better than me, so maybe he can say. But in these papers by Rastelli and collaborators, for instance, the recent ones.
I see. So I mean, so basically, the question that we set out is that so let's think about. So we have the contact term for 2 spin s and 2 graviton.
Right.
So is this operator fixed by some physical principle?
Right. And suppose the physical principle I want to propose is that there's of course the 2 spin s, then graviton splitting to 2 gravitons. That's the exchange diagram.
Right. That one, yeah, that one we know what it is.
That we know what it is. That's unambiguous. And then there's an infinite ambiguity in the contact term.
Exactly.
But higher and higher, if we choose a finite series of these contact terms, we will in general have higher and higher Regge growth behavior.
Right.
So what you try to do is to choose the contact term so that the net amplitude grows as softly as possible in the Regge limit.
Right. Right. Yeah. Yeah. Actually, yeah. I agree. Yeah. But yeah. So we. Yeah, that's also something that we're looking into. So of course, first we have the parameterization of all the possible contact ambiguities.
Yes.
And it's basically looking at the high energy behavior and what actually has the best high energy behavior in terms of.
But high energy in the Regge limit.
Yeah, in the yeah.
Large S.
Yeah. In the small angle limit. Yeah.
Yeah, that sometimes turns out to be the right thing. I wonder if it turns out to be the right thing for black holes.
That'll be interesting. I mean, so interesting to actually do this and to fix what actually selects, because as I mentioned, there's no gravitational computation that we can match to yet, because there's still so this actually comes out at s to the 5 order, because that's beyond spin 2. We need some where this ambiguity starts to kick in is when you go beyond spin 2. And for them, the gravitational community has only computed up to s to the 3rd power, which will correspond to spin 3 halves. But yeah, that will be something that will be nice to figure out, to see if actually uniquely selects 1. I kind of suspect it will not uniquely select 1, but yeah, I haven't really done the analysis.
Okay, yeah, I'm not sure.
Yeah.
So here we are talking about the 4-point amplitude for black hole, and two gravitons. Is that what you're talking?
Yes.
I see. Yeah. I mean, the uniqueness thing, to my understanding, comes from the fact that you are simply looking at the behavior of the amplitude in the Regge limit, and there's some polynomial dependence, and you just subtract that polynomial off. So that
So I
you
guess
have the softest.
the statement is that in the Regge limit, there's a unique one, the unique combination of these contact terms that gives you the best soft behavior.
Yeah. See, so you can suppose you have something that grows in a certain way in the Regge limit, and it's relatively soft. Then you add a high enough degree polynomial, it will grow faster. So even if there's some ambiguity, it'll be some small ambiguity. It won't be an infinite ambiguity.
Right. Yeah, and maybe that I mean, maybe it doesn't even have to be unique, because that the non-uniqueness will be irrelevant for the long-range physics. That might also occur.
But even this principle, I don't know if it's the right one, but even if it does give you a uniqueness, it'll be ambiguous. It'll be like with 3 parameters or something like that. It won't be very much.
Yeah, I agree. Yeah. It will be finite number. I mean, especially, it will be finite number. I agree. Yes.
You should go on, but when I first asked you this, I had in mind something much more simple-minded, that if we look at the geodesic deviation way of trying to compute higher orders, and now you've told us that both Schwarzschild and Kerr have a Kerr-Schild form where you make certain changes. Does that automatically tell you something, just thinking like that, about higher orders? But I'm sure you've thought about it. I'm sure it's not very simple to try and set up something obvious that way. But anyway, that's all I sort of meant. But
yeah, certainly I haven't thought about. Yes, that's just if we can do the geodesic. Yes, so if we can, one of the things. So one of the things that we are in an initial stage of doing is to take, of course, the geodesic deviation equation. We can use that to get the next order impulse, and then try to match it with the amplitude, where the amplitude is parameterized by these ambiguous contact terms, and to see if along the way that we can have if we can have a matching. And because I don't know if doing this. I haven't really done this, because I have doing along the way, there might be some limits that are ambiguous. But if we can do the matching, then that in principle should select the contact terms for the matching, indeed. But I'm not sure if there might be complication that comes out, because I haven't really thought about this at the next order yet.
Yeah. Okay. Thanks. Thank you.
Sure. And I suspect that there's some complication, because otherwise the GR community would have already done it.
I see. Okay.
So that's
Right. Thank you.
Sure. Right. So let me just go along. So we see that this exponential in phase. So this exponentiation in the spin factor actually generates the Janus-Newman shift, which is related to going from Schwarzschild to Kerr. So now you can think about, is everything, all the different black hole solutions, generated by something that looks like this? And if you think about it, you can think about what kind of things that can exponentiate on a 3-particle. And if you look at the kinematics, because you know that P dot Q is 0, and actually P dot S from the definition of S, because S is the Pauli-Lebensky vector, is also 0. You realize that actually the very first thing that we exponentiate is actually the only thing that we can exponentiate, other than a complex phase. So the other thing that you can do is just take X and do an exponentiation and generates a complex phase. And we actually know very easily what this complex phase corresponds to. That corresponds, if this is an electric coupling, that corresponds to generating the coupling of a dion, because if the electric charge would be, if the electric charge is the original real coupling, then the magnetic charge would be imaginary, and the complex charge would be the dion. And therefore, you might think that, okay, so since if I accept that X going to exponential I theta corresponds to dion coupling, then there should be something that corresponds to the double copy of that. And if we look through the literature, there's something that is sitting there waiting for us. That is the Taub-NUT spacetime. And you might ask, does this generate the Taub-NUT spacetime? And indeed it does. And so that we can just go through the computation. It's very enlightening. So I'm just going to go through this and real quick. So first, let's verify that the dion corresponds to this phase shift. So once again, we're just looking at the impulse, where in the E&M case, the impulse, we can just compute it from the Lorentz force. If it's a dion, that means that the Lorentz force, the F field strength here, so this is just undergraduate computation. We just have the electric charge and the magnetic charge of sources, the B and the E field, which gives us the field strength. So the field strength in momentum space will take this form. So we can plug in the field strength into the Lorentz force, and the Lorentz force gives us computation, gives us exactly this answer for the impulse. And all we need to do is to match this computation with this, and you will find an exact match. And you'll find that the Q is the cosine theta, and the Q tilde is exactly the sine theta. So this tells you that indeed the dion, this gives you this shift in the 3-point amplitude, this phase shift gives you the dion impulse. Right, sorry, this is precisely the computation. So this is the W is the rapidity, and then after the computation, we can have the direct match. So if we take this and then we take the double copy of that, which means that we're just double copying the phase, what that tells us that the impulse is now going to give something that is similar to the dion, except that the rapidity dependence goes from omega to 2 omega. And you can see this, and we can match this directly by doing another computation, which is doing the geodesic equation in Taub-NUT spacetime. So this is the usual Taub-NUT form. And since we're doing a 1 p.m., we can do a linear approximation to this, and we get the linear metric. And from the linear metric, of course, we can just go through. This is a usual textbook computation. We compute the Christoffel symbols. And once we have the Christoffel symbols, we just plug in the geodesic equation, which in this case, we can massage it in a very nice way because we're really at linear order. And so you can identify a scalar potential as H0 and a vector potential, it's H0 I. Then you can convert the original thing into something that looks like the Lorentz force equation. And so this almost is a Lorentz force, except that in front of E and B, there's actually a factor of cos 2 omega time over cos omega and sinh 2 omega over sinh omega. But this is exactly the Lorentz force form. So all you need to do to compute the impulse is just take the original Lorentz force and then multiply the Q and the G charge by this extra factor. So if you multiply this to the usual Lorentz force equation, you exactly get what we get from double copy. So this shows that this double copy, indeed, this phase shift in double copy indeed gives you the Taub-NUT spacetime. So we see that the double copy of dion gives us the Taub-NUT. So this indicates that first, number one, the Taub-NUT metric is again some kind of complex shift acting on Schwarzschild metric. And furthermore, this shift should have some interpretation as an electromagnetic duality transformation, because we know that a single copy is an electromagnetic duality transformation. And indeed, first of all, indeed, this is a complex shift, because also not long after Janus and Newman had the realization of Kerr from Schwarzschild using the Janus-Newman shift, Taub also generalized that complex shift and showed that you can generate Taub-NUT spacetime from that shift. So in the retarded coordinates, you can just shift U to U prime with this complex shift here, and R to R prime, and with the shift in terms of the mass charge. And this generates the Taub-NUT spacetime solution. So this was found by Taub. And more recently, this complex shift introduced by Taub can be viewed as a generation of BMS supertranslation. So this, so let me just give a quick review here. So if we do an expansion of asymptotic flat metrics around future infinity, it generally takes this form where the unfixed information is these CZZ, CZ bar functions, and the U functions are derived by CZZ. Gamma is the two-sphere asymptotic infinity. Now this metric is invariant under BMS translation, which acts through this differential operators by an arbitrary F. For real F, if F is a real function, then this is just a symmetry of the metric. And so because you have this the symmetry, of course, you have the corresponding charge, and the corresponding charge is just written as this form integrated over the two-sphere. So So last year, more recently, one of our collaborators, Uriko and Massimo, they showed that this shift that was introduced by Taub-NUT is actually a BMS shift, the BMS supertranslation. But so they showed that the Taub-NUT matrix has a CZZ that takes this form, and this form is generated by acting on the Short-Shell solution via imaginary supertranslation. So remember here for real supertranslation is a symmetry, but because this is imaginary, so it's no longer a symmetry, it generates a new solution. In particular, the FZZ bar, the translation function takes this form to IL log sine, and this is the differential operator that corresponds to that. And so this generates the Taub-NUT solution. And if you look at what this translation acts on the BMS charge, and they realize that, so first of all, besides the usual BMS supertranslation charge, there's actually, they define a dual supertranslation charge, which is defined in this way. And they show that that translation, when act on the dual supertranslation, generates a complex shift, where the complex shift result is exactly the dual magnetic charge, the dual charge associated with the Taub-NUT solution. So indeed, this complex shift modifies, you can say that it is exactly an electromagnetic duality. It's a duality associated with the supertranslation and a dual supertranslation charge. And actually, you can see this in a more transparent fashion if we use the the Newman-Penrose formalism. So as all of you know that in Newman-Penrose formalism, we basically decompose the wild tensor into 5 pieces by contracted with these vectors. So L and N, these all are null vectors, and they actually have a very nice spinor helicity interpretation. So for L and N, they're just basically random. They're just basically some null vectors, and M and M bar are just the complex modifications of these null vectors. So they're using the same lambda and lambda tilde and rho tilde. But anyway, so if I use this language, use the Newman-Penrose decomposition. Of course, we know that there's psi 0 to psi 4, and each of these have different asymptotic behavior in R expansion. So these are actually the near region, so they die off very fast. These are the potential, and these are the radiation. And in this language, you can see that the BMS charge, supertranslation charge, and the dual supertranslation charge is just the imaginary and the real part of psi 2. Okay, so we identify this as psi 2. Then if you look at, for example, I'm going to do the full Kerr Taub-NUT. If I look at the full Kerr Taub-NUT solution, then the psi 2 takes a very simple form. This is just how it looks like for Kerr Taub-NUT. And if I do linearized version, which means I'm doing linear to M and L, then it just takes this form. So indeed, you can see that for psi 2, the Kerr Taub-NUT solution is just electromagnetic rotation, because it just rotates from M with an extra imaginary part. And this extra imaginary part is generating something that has originally just dual translation to just originally from just the charge for supertranslation to dual supertranslation. So this is what corresponds to that complex shift, the electromagnetic duality. So at this point, you can consider all the different possible black hole-like solutions. So now we have a complete description of all the possible black hole-like solutions in 4 dimensions in terms of just minimal coupling. So we can differentiate this. So for a Short-Shell, it's just the gravitational coupling. For Reissner-Nordstrom, it's gravitational minimal coupling and electromagnetic minimal coupling. For Kerr, you have this exponential and spin. For Kerr-Newman, we have this exponential and spin both in the gravitational sector and in the electromagnetic sector. And for Taub-NUT, you just take the Short-Shell solution and do this exponential and phase rotation. And for Kerr Taub-NUT, you take the exponential phase rotation and the spin. And that's basically all in this, actually nicely matches to all the classical solutions that we have in 4 dimensions. And this also gives you a very nice relation between all the different solutions and linearized order in terms of 3 operations. So first, this yellow line is the spin, which is the Janus-Newman shift, which is this exponential and spin shift. This is the duality. The green line is a duality, which is the exponential phase shift. And this vertical line is the double copy. So now all of the solution has, at least at linearized order, are all related to each other. So if you start from Shortshell, you did exponential spin, you get Kerr. You do the phase, you get Taub-NUT. And these I actually commute at linearized order, and they give you the Kerr Taub-NUT, and they have their single copy version. And actually the single copy version also corresponds to when these black hole carries charge, and their electromagnetic coupling are coupling through these single copy version. So yeah, as Shiraz asked, it will be interesting to see what this picture becomes when we consider higher dimension solutions. So I went through this a little bit fast because I really want to come to the last part, or more like the second part, which is what is this minimal coupling telling about Kerr? We've answered a few, but those answers basically tell us some of the things that was already observed in the past. But we would really like to ask is what is the physical principle that select these couplings? Now, one statement is that in high energy limit, if we consider spin 1, spin 1/2, and spin 2, these actually match to the couplings of lowest derivative orders when everything is massless. But this interpretation is only valid for the cases when S is equal to 2 or lower, of course, because we don't have massless higher spin particles in flat space beyond spin 2. Now you might say that oh, these couplings are special because if I look at the couplings here, this is of course special because this is simple and all of these G's are not there. But actually this is not entirely true because I cheated a little bit here. And the way that I cheated was that in the very beginning, I know that these things look simple in this spaces. So what is this spaces? You notice that I'm in alpha and beta and not alpha dot and beta dot spaces. I can convert this into alpha dot beta dot space. And the anti-chiral basis, actually it's not simple in the anti-chiral basis. It's actually simple in the chiral basis. The reason it's simple in the chiral basis is related to the fact I'm coupling to a positive photon. If I let it coupled to a negative photon is actually not simple in the chiral basis. So if you think that the physical principle behind selecting minimal coupling is simple in terms of form, is actually not entirely true. It depends on which basis you look at. And so instead of looking at high energy or low energy, or whether it's a chiral or anti-chiral spaces, we turn to looking at entanglement. So basically, you can consider the 2-to-2 scattering process as some in state coming in and some out state going out. Of course, then the out state corresponds to the information of the S matrix acting on the in space gives us, in particular, the out space. So if we would think about it in this way of a scattering event, then of course the natural thing you would do is to talk about entanglement, because then we just compute the density matrix, trace out, for example, trace out particle B, and then with the reduced density matrix, we can compute the von Neumann entropy. And then the natural thing we can ask is, let's say if you have some in state with some particular entanglement, how much entanglement is generated through the scattering process? In other words, what is the difference between the entanglement entropy of the out state with the in state relative to the in state? Now this, of course, we're not the first people who thought of this. Has been going on for a long time. And usually in trying to talk about entanglement in the scattering amplitude is plagued by various different technical difficulties. For example, if you're talking about scattering amplitude, mostly what the problem is how to characterize what exactly is the Hilbert space you're interested in. So if you're talking about the Hilbert space parameterized by momentum, then of course we immediately have the problem that we're in flat space. And so therefore, most of these things are divergent. So you have infinite volume problems associated with the Hilbert space, and that requires regularization. And then the answer that you have depends on the particular regularization you choose. Now instead, of course, you can instead of not think about momentum space, but trace over spin space. You're thinking about these particle carry spin. So let me just look at your spin Hilbert space, and then let's just trace over those spin Hilbert space. But then you have another problem, which is that the spin space in here of the in states are different from the spin space, Hilbert space of the out states, precisely because, as we know, that the little group, which defines through which we define our spin space, is actually defined relative to the momentum. And since the incoming momentum is different than the outgoing momentum, the Hilbert space are distinct. So this is not really well defined. But actually, this issue about the Hilbert space is not distinct. This problem is actually already been dealt with a while ago in the gravitational community when we're trying to compute these potentials, or which is associated with the conservative part of the Hamiltonian. And remember that once we have these, we are computing things using these effective in this one particle effective action. We have these operators, and as I mentioned, if you want to compute these, you can sandwich these operators with polarization vectors, and therefore these 3-point amplitudes will corresponds to some operator coefficient sandwiched between polarization vectors. And if you want to compute, then we can compute the potential using these 3-point amplitude. So in principle, you just glue these 3-point amplitude together, and then you compute the 1 p.m. potential. But however, as I mentioned, that this potential is really about the potential in some Hilbert space, and particularly if we think about the spin Hilbert space, then these spin Hilbert space are distinct from this spin Hilbert space. So you actually need extra factors here. These extra factors here are what we call Hilbert space matching, which basically are just Thomas-Wigner rotation, which translate the Hilbert space for the outgoing back into the Hilbert space that are set up in the ingoing. And these are just basically a series of Lorentz transformation, which I won't go into any, which is just the usual Thomas-Wigner rotation factor. But these are actually known, and we've computed to all orders in spin. And just to show that that what we've done is correct, so we computed the explicit Thomas-Wigner factor, which is depending, of course, on the spin vector. And so we've been able to generate the 1 p.m. potential for a general spinning body with these arbitrary Wilson coefficients to arbitrary order. And since the GR community has only computed to particular order which they're interested in, so we've been able to match at each order which they computed. And but for all of these, we've already have the complete answer. So this shows that this.
You said this, but is this just exactly the boost that would take you from P1 to P2?
Yes, that's related to that boost.
And is it exactly that, or some more?
So it's really the rotation part of that boost. So if we set up P1 to be in the rest frame, then that would be at that boost. I would need to extract the rotation part.
Yes, and of course this boost is ambiguous, so that there would be some ambiguous phases. Because you can rotate in the direction that your vector is. You can perform the rotation that leaves P1 invariant.
Right. And yeah, exactly. Yes.
But you don't care about those phases.
Yeah, those will drop out. Yeah.
Okay.
Right. So good. So very good. So once we have this, this rotation factor, then we can plug it in and get the 1 p.m. potential, which is just what I mentioned before. Good. So equipped with this boost, then now I'm really talking. So now the computation that I set up is we have some in-state and we have the S matrix, we have the scattering amplitude, and then we do this boost factor, the Thomas-Wigner rotation, to rotate everything back into the same Hilbert space. Now the out-state are defined within the same Hilbert space as the in-state in terms of spin space. So now I can legitimately compare the von Neumann entropy of the out-state compared with the in-state. So of course, there's another thing that we can do is we can compute what is called an entanglement power. Which is basically also computing the trace of rho A square, and then we integrate over all the possible in-state configuration. So of course, the reason that one would want to look at the entanglement power instead of the entanglement entropy is because for the entanglement entropy, we need to compute the difference between the out state and the in state to really get the information about how much entanglement is generated. And you might say that computation alone might depend on the particular in state that you're doing. And so some people will define this entanglement power, which integrates all possible, which averages over all possible in state configuration as a way to discuss how much entanglement is generated. But as we'll soon see that this is actually, these two will get the same result using these two observables. Okay, so now we've set up our computation. So we consider a 2-to-2 S matrix. And of course, we have the first 1 p.m. or linear order computation, and we do the Fourier transform and get the econo phase. And then, as I mentioned, as Abhijit asked, the natural thing is to exponentiate this factor, which corresponds to, in the econo limit, that there's this all loop sum that we have here. So then we get the econo S matrix. So once we have the econo S matrix, sorry, this is just a few details about how the computation was done. Let me just skip this. So basically, after we do this, we have that first we write the tree amplitude down in terms of these parameters A, and multiply by these T factors, where these T factors are basically the spin vector dotted into Q. So these are matrix elements. These are matrices. And these A factors are now parameterized by the Wilson coefficients. So, right, so these are the different Mn here corresponds to the different spin vectors, the powers and spin vectors we have. And so basically, when you compute the tree amplitudes, it's going to be parameterized by these Wilson coefficients. And then we compute the econo phase, and then we exponentiate it. So once we do the exponentiation, then we can start to compute the change in entanglement and entropy. So this is the plot. For example, let's start with spin 1. So for spin 1, the relative Wilson coefficient, there's just 2 coefficients at spin 1 that is unfixed. And we plot the entanglement entropy change, the change in relative entanglement entropy.
Just to make sure I'm understanding, the Hilbert space that you're working with in this entanglement entropy business, is that of 2 spinning particles?
Yes, 2 spinning particles, spin A and spin B.
Right, so if the spins were finite, this would be a finite dimensional Hilbert space.
Yes.
Thank you.
So for spin 1, because we have 3 components, so this is a 3x3 computation, 3 times. So all of these, right. So, okay, maybe I should go into a little bit detail here. Is that the degree corresponds to what the spin operator acts on, or for spin 1, this will be a 3x3 spin operator, a spin matrix. For spin 2, it'll be a 5 times 5. So we have 2 Wilson coefficients here, and so you can compute the entanglement entropy, the change in entanglement entropy. So this is a particular plot. So these are just the numbers where we plug in for the kinematics, and you'll see that for the Wilson coefficients, first of all, the 0. So there's the minimum here, and the minimum.
Sorry, Newton.
Yes.
Won't your entanglement entropy depend on your scattering angle?
The scattering angle, these coefficients are just sorry. Let me think. Sorry, no, there's no scattering angle because these are just. So let me just go back here. Yeah, because we're taking Q squared to be 0. This is an econo limit, so there's no. So in other words, in the 4-point amplitude, you have S and T.
Forward scattering.
Yeah, so this is really the 4 limit.
Okay.
Yeah, that's why you can do the econo approximation.
Right. But in general, if we wanted to compute just the 2-to-2 scattering matrix, you'll get a different entanglement depending on the scattering angle. Yes,
but then then there's a problem about because we want to do a linear order in G, where this approximation is completely, so if generically, right. So the statement is, so the reason that we do, so I mean, for one thing, that one could have just done this and not do the econo phase, just look at the amplitude, a leading order in G. And then what the issue that you'll find is that in principle, you'll see that there's a unitary violation, which you know what's going on because we're doing a perturbative expansion in G.
Okay.
Because it's not really strictly unitary. But once in the 4 limit, we could this naturally exponentiate it, and then we can have a unitary S matrix.
Okay.
Because it's just exponential of the right.
But in general, you could just take that e to the power it and exponentiate it. That would give you the right answer to leading order in T and would be unitary.
Yes.
Yeah. Okay.
Okay. Right. So the point is that if you see that there's actually a minimum occurring exactly at when the Wilson coefficient goes to 1. This is exactly the minimum. And the change in the entanglement entropy is very small, so it's 10 to the minus 9, where so there's orders of magnitude away from the minimum. And actually, so this minimalization is independent of whether you throw in a pure state, what kind of pure state, or if you throw in a mixed state. So we computed the different kinds of incoming end states, and they all give the same minimization at this point. We also compute, as I mentioned, the entanglement power, which averages over the end states, and you also get the minimum. Now you might say that this minimum is not really too dramatic compared that there's really a large flat region around here. But this is just the artifact of we're just focusing on spin 1. If we go to higher spins, so this this sheet starts to get raised up. So for example, for spin 3, where we have 5 Wilson coefficients, now you see the dramatic minimization here. So since we have 5 Wilson coefficients, we can't really plot multi-dimension for all of these. So we just consider various pairs of Wilson coefficients and deform away from the spin 1 case. And we see that for all cases, spin 1 minimizes the entanglement entropy change, and it minimized very slow. It's always around 10 to the minus 8 and 10 to the minus 9. So for us, this result is really, well, at least for us, it was very surprising because we're basically what is happening is that you're setting up a scattering event, and you're doing multiple exchanges. And so somehow through this multiple exchanges, there's no entanglement when the Wilson coefficients are set to black hole coefficients.
So is the entanglement 0?
No, it's not 0. So once again, I'm talking about the change in entanglement. So if the initial entanglement, the in state has a particular entanglement, the out state will have almost exactly the same entanglement.
So suppose you started with the pure state for the 2 spins as the in state.
Then it's going to be the pure, almost pure state at the end.
So it's 0 at the end. The entanglement entropy is 0.
Yeah, it's not strictly 0 because this is 10 to the minus 8. But
you think that's numerical error, or you think that it will be strictly?
This is not numerical error. It might be that because I mean, of course, we're doing economic approximation, and we're still doing expansion in G.
But sorry, go ahead, Shiraz. I had a follow-up to that.
Yeah, I just was wondering whether it's possible to have non-trivial scattering with 0 entanglement. I thought that sort of was impossible.
Yeah, so that's how we phrase. So it's that's how we phrase. If we want, we were asking that if there is an S matrix that gives you 0 entanglement, 0 increase in entanglement, then it appears that this black hole S matrix is the answer. Because we can search in this space and try to find the minimal point, and the minimal point exactly corresponds to all of these Wilson coefficients being 1.
Yeah, I was saying something more stupid and probably more wrong, which is that I had thought that an S matrix that does not produce entanglement, if you start with 2 pure states and then you do not produce entanglement, that would be the trivial S matrix.
Yeah, that's what I thought too. Yes, exactly. But this computation shows you that there's some S matrix that is not 0. But the entanglement that it generates is
well, maybe because you're looking just in the forward limit or something like that.
But as I mentioned, that if you change the Wilson coefficient away from C equals 1, any change of the Wilson, then it's no longer 0. Right. These are all forward limit computations.
Yeah, no, it does seem incredible and very dramatic, but it just seems to me to be impossible that you produce no entanglement completely.
Sorry, why is that, Shiraz? I mean, why can't you apply a rotation together to both spins?
If you produce no entanglement, it's like you're doing a unitary separately on each of the 2 particles.
Yeah.
And that is basically no interaction. You're just doing what happens in one particle and the other particles. Somehow there's no mixture.
Yeah, so one of the things that we were trying to see is that whether or not that we can actually write that econo phase into a factorized form, so that this 0-ness is manifest. In other words, yeah, so the S matrix will be just a factorized 2 unitary operator acting separate.
So, sorry, Yutin, I had some internet problems. You might have already said this, but I wanted to ask you the following. Does this somehow mean that the spin flip amplitude is suppressed? If you start with an unentangled state, you're saying for the choice of Wilson coefficients, let's say it's a product state. If you have 2 spin ones, it's just up. You're saying that whatever state you end up in after maybe a suitable rotation to align with the momenta, it's again unentangled for this choice of Wilson coefficients, if I understand you.
Yes. Yes, so the entanglement entropy will still, if it's a pure state if it's a pure state, then the final entanglement entropy will still be close to a pure state.
So I was just wondering, I'm sure it's not as simple as this, but suppose I think about it from the rest frame of the heavy particle, one of the two heavy particles, which is say spin up, it emits a soft graviton. Is there an amplitude for that spin up to become spin down, which is non-zero in your limit? And despite that, at the end of the day, the state remains unentangled? Or is it just, I think it can't be as simple as this, or is it just that, you know, the spin flip part is suppressed in some sense? I suppose there's a non-trivial amplitude, but it's still resulting in no entanglement.
Yes, actually, there's something that is related to that. Yes, if you have minimal coupling.
Yeah.
Yes, indeed. So this is associated. So if you have minimal coupling, then there's a selection rule for this is just going to the high energy limit. If you go to the high energy limit, if the incoming is plus minus, then the outgoing has to be plus. There's no plus plus configuration for minimal coupling. To generate a plus plus configuration, you need non-minimal coupling.
Okay, you know, because in electromagnetism, in QED, the sigma dot B coupling is suppressed by the mass of the particle, right? And this is also true in heavy quark effective field theory. So I'm just wondering if there's an analog here that's sort of explaining it at some level. I'm not sure, but that the minimal coupling just doesn't like spin flips so much. I don't know.
At the individual, yes, but because well, first of all, we can't really do that analysis because first of all, the only non-trivial thing starts to happen at spin 1, where you don't have just spin up and down. So you have.
No, I understand. I understand.
Yeah.
And you're saying for the minimal coupling, that is your choice where you're getting the minimum. There is an amplitude at this order for spin flip, and yet at the end of the day, if you start with unentangled initial state, you end up with an unentangled initial state. Huh? Is that what you're saying?
Yes.
Yeah, that is pretty interesting, isn't it? So if there's an amplitude that the spin, let's say you start with both as Sz equal to 1, you go along, the Sz equal to 1 becomes something else, let's say down because of the exchange, the other one will also only become down. It won't be any linear combination.
So for the amplitude level for M, so for just the tree amplitude, there will be sign flipping, yes. But because this is no longer just tree, we're doing the entire resum result.
All right, then you iconoloze. Yeah. Then you have to do the multiple guy. I see.
So it's a little bit more subtle than just the single graviton exchange picture.
Can't you say you can't ask that question with just single graviton? You have two initial and two final states, and you decide somehow on how to compare the spins in the rest frame, your little group thing. You can't do that. You really need to iconoloze it, just because you can still ask the question, of course. But
I can certainly still ask the question. Yes, I can ask the question. Of course, there's so first of all, well, the reason. Okay, so we can consider the single exchange, but then first of all, because we're looking at q squared go to 0, which in principle in momentum space that gives you a singularity because of the q square pole.
But that we sort of can take away, I don't know, by saying after some time the scattering ends or something, like we do for Coulomb scattering.
Yeah, but for Coulomb scattering, what you do is exactly you Fourier transform to position space.
Yeah.
Right? And so that's what and when you Fourier transform, and that gives you the econol phase.
Okay.
And that phase, the natural thing is to exponentiate.
Okay, so if that's what you're saying, then that's fine. I would have said, okay, that's still Coulomb scattering, but let's say you're gone to position space and you're taking care of the 1/r kind of effect.
Exactly. Yeah.
Right.
The more systematic.
Okay, good. And there, roughly speaking, then the picture is that yes, you start with two spins unentangled and end up with spin flips, but still unentangled states.
Yeah, we should have looked at it a little bit detailed. Sorry, I mean, yeah, we should have looked at actually what is the end state looks like. Yeah, we just
it's
plug
very
in.
interesting. Yeah.
Yeah, we just plug in and just compute the entanglement. But yeah, that's an interesting thing. We should look at how the spin ends. I mean, how exactly does, if we have a pure state come in, how exactly the end thing look like?
Yeah.
Well, if it's unentangled, aren't you saying that how the spin of the first guy flips is independent of how the spin of the second guy flips? Because it's like a product of two unitaries acting independently on the first Hilbert space and the second Hilbert space. So that
From
the second spin is not affecting how the first one flips.
That is the more correct interpretation, Shiraz.
Yeah.
That's
so
right.
It feels like you're saying there's no spin-spin interaction. Because if there's a spin-spin interaction, then how the first guy flips is affected by what the second guy is doing.
Yes.
Yeah. That's
so even right. So, but of course, if you look at the amplitude, there is spin-spin interaction because you can even see it here. Let me just, if there's a nice way.
Shiraz's way is the correct way. I mean that you can flip, but there's no interaction in the flipping. That's correct. Go ahead.
No, but Sandeep, the way you said it with the 3 points, that also was, I mean, if the spin flips at the level of a 3-point interaction and a graviton comes out, then it will affect the spin of the other guy, right? So in that sense, they will be correlated.
That's also true. Okay, but go ahead.
Yeah, but you can, exactly. So you can see, so the basic is that this amplitude has these A00, A11, A20. So A21 is, for example, the spin operator of one leg to the second power coupled to the other spin vector operator. So they always have spin-spin interaction at the amplitude level. And
so is it that when you set C to 1, there is some cancellation between all these operators?
Well, certainly if you set C equals 1, these are not 0. These yeah.
I'm just wondering whether the forward scattering limit is something special. That if you looked at all theta, you wouldn't see the 0. It just seems somehow impossible.
Yeah.
Yeah, I agree. But yeah, I think so. I agree. I think that if you go away from the forward limit, of course, we haven't done any computation in that limit. But really, we're just saying that we're just looking at in the forward limit, what's special about C equals 1. So that's basically the question we're asking.
Okay, thank you.
Also, in the forward limit, you don't quite need these Thomas-Wigner factors, right?
No, you still need that to, you still it's still non-trivial. It generates some non-trivial factors. I mean, that's why that's one of the reasons we talked about this, which is that once you need to have the right rotation factors to match with all these classical GR computations.
And these factors are not affecting entanglement, right? Because they are separate.
Yes, that's true. Yes. Because they're in other words, they're independent. I mean, they're independent of the Wilson coefficient. So if you tune the Wilson coefficient, it's not going to change anything for these guys.
Okay.
I had one other thing, although I must let you go on, sorry, which is, you didn't keep the momenta in thinking about entanglement because you said that would give rise to divergences.
Yes.
But, in a sense, there is a divergence when you think about the vacuum itself and you try to split it one way or another in position or, let's say, momentum space. But over the vacuum, you're only adding a few particles. So if you were to compute literally the relative entropy in the in and out state, I suspect you should be able to get a UV finite quantity even after you keep track of momentum. And that might be interesting. I mean, it'll be technically a little challenging to do, but probably not so challenging. And then you'll sort of get the full picture of entanglement, not just the spin part.
Yeah.
But anyway, I just thought, I think technically the relative entropy, not a comparison of the entropy, but what's called the relative entropy given any density matrix, two density matrices, that quantity should be finite, I think, and not too hard to compute. Anyway, that's just a aside in that it might be interesting to see how that behaves.
Sandeep, could this be basically doing his computation as a function of theta and then integrating over theta?
No, I was thinking, you know, Shiraz, even for any particular value of the final state, you know, we have two initial momenta and then two final momenta. And we should be able to compute the entropy in the final state if we are looking at one of the two particles and compare it with the entropy in the initial state if we look at one of the two particles, or whatever comparison he would like to do.
Right. And I was wondering, in the end, be the following: the two particles are separated, have some relative momentum and some spins. And I was wondering whether, in the end, this will amount to computing what he's doing at any given momentum and then integrating over the angle separation.
Yeah. There is an overall momentum correlation because total momentum is 0 that we take out, and it's kind of trivial. And it's trivial. Over theta. Yes, and then it's only the angle. That's correct. But that's correct. That's correct.
Can I make a comment? This is Aninda here.
Oh, yeah.
Can I add to Sandeep's comment? Yeah. So I agree with Sandeep, because actually we did the calculation for relative entropy for to do scattering in the context of S matrices, in particular keeping the S matrix bootstrap in mind. We did exactly what Sandeep was suggesting.
I see.
And I think I also agree that instead of computing the difference of entanglements, it makes more sense to calculate relative entropy.
Okay.
And relative entropy becomes, it's a very nice physical calculation as well, because you can do hypothesis testing and things like that. And it would be a function of the angle as well as the momentum.
Yeah.
The question about, I have a question about the trying to integrate over the scattering angle, because here, of course, we have the massless pole T, right? So you know that in the integration, you're going to have a divergence. So we literally just take the amplitude and just integrate it over the scattering. There's going to divergence coming from the T pole.
From the T pole, okay. Because of the long range nature of
the
force, we'll have to think about how to control that. But I don't know, Anindya, did you must have thought about conformal theories. Anyway, we should allow.
We were looking at the S matrix bootstrap. So we wanted a selection principle very similar to what Yutin is trying to do, but for the bootstrap.
Okay.
Sorry, Yutin, your divergence would be from this point of view of integrating over theta at theta equals 0?
Yes, the exact theta equals 0. I mean, if we just have the amplitude and not do the Fourier transform, but just literally just integrate it.
So the T pole.
Yeah, it's the usual T-pole obstruction and trying to do Fourier analysis just directly on the amplitude.
Yeah. So these are the IR effects of gravity, the fact that gravity dies off very slowly.
Yeah.
Okay, thank you.
Yutin, are you going to explain this more? So is there an intuitive picture as to why you expect this measure, this entanglement to become minimum? So long time back, there was a paper by Zurek, and the question that he was trying to address was in a quantum mechanical phase space, why is it in real life do we see coherent states? Is it a consequence of decoherence or not? And the answer was yes, and there was some minimization that he had prescribed. Is it related to that? Why should entanglement be minimum?
Yeah, so sorry, I'm not aware of that paper, sorry. And we right now we don't have, we still don't have, other than like very hand waving way of saying like the interactions are the simplest, and therefore they in some sense we do expect that it generates the minimal entanglement, in the sense that these interactions are the simplest interactions that one can have. But why is it so close to 0? We don't know.
How do you categorize simplest? I mean, is it just that some of the coefficients become 0 in some coordinate? Is it a coordinate system dependent statement, or?
Yeah, exactly. So that's what I just previously said, that in the spaces that I wrote down, they're the simplest because they don't have all these higher moments.
Mm-hmm. Okay, thank you.
Okay, so I guess that's a good point for me to end. So I hope we've seen that in terms of this on-shell basis, that there's a lot of properties of black hole solutions are cleanly captured. The minimal coupling itself generates all the black hole multiple expansion. And then we've seen that the potential physical principle behind this choice of minimal coupling appears that there is a near zero spin entanglement. So right now we're looking at other extensions from this. So what is the story beyond leading G? So we're now analyzing the next order econol phase and looking at how entanglement behaves there. And of course, we note that just like in QED, we have anomalous moments. So we can ask, is there anomalous multiple moments? So we have that if something that has minimal coupling to begin with, if we consider quantum corrections to that minimal coupling, is that minimal coupling still going to stay minimal? Is there going to be any anomalous moments? Is it protected in anyhow? And we of course, we would like to also look at charged black holes and BPS black holes. In other words, if we look at SUSY black holes, and does the BPS limit correspond to some special limits, and also in this entanglement phase and entanglement analysis. And of course, this analysis of the multiple moments there's really a lot of recent work on analysis of these multiple moments from black hole microstates. And once we have it, so anytime the same as we have these multiple moments and specific computing, we can always throw it into this spin entanglement analysis and see if there's any interesting features that might come out of it. Yeah, so I think, so thank you very much for the attention. I think that's a good place to end. Thank you.
Thank you very much, Yutin, for a very nice talk. Let's all unmute and thank Yutin again.
Thanks, everyone. Thank you for the very nice questions.
We have quite a few questions, so if there are questions, yes, please go ahead.
Can I ask a sort of a simple-minded question? So suppose I wanted to study a similar problem for the Mercury, Mercury going around the sun. Yeah, using these kind of principles, would we be able to get the Einstein value for the precision? Do you think?
Precisely because that if we could consider Mercury going over the sun, that corresponds to the sun. So let's say Mercury is a probe, and well, actually, so these corresponds to different C's, right?
Yes.
So then, of course, they won't be minimum. So in other words, you'll get non-trivial entropy. That's what one would expect. If we actually compute this behavior of if you have sun and you have Mercury, then the Wilson coefficients are not the black hole coefficients, and then you will expect that we have non-trivial entanglement.
But yeah.
Is that what you're asking?
Yeah, I mean that is what I was asking. But can't we model the external geometry as some linearized approximation to Schwarzschild? I see Sandeep is nodding his head. I mean,
but the spin multiples are different. So the spin multiple of the sun is going to be different than the spin multiples of a black hole. So that's the statement.
Mm-hmm. I see.
If I can just come in, I forget the details, but I think just first order in post-Newtonian is enough for that perihelion shift, right?
Yeah, yeah.
So there is a way to incorporate it sort of systematically as a correction, if that's what you're asking. Of course, you know that, Anindya, but we can then try to convert it into this language, perhaps. I don't know. I'm sure.
I mean, it's just that, yeah. I mean, it's directly just a statement that for Mercury and Sun, we're going to have different C's, and this is first post-Minkowskian.
Okay, post-Minkowskian, I guess.
Yeah, and if you want to do post-Newtonian, that means that you're further expanding in S. So higher order in S corresponds to higher order in post-Newtonian.
Okay. Yeah.
Sorry, I thought the spin of these bodies don't quite play any role in this.
Yeah.
Precision.
Yeah.
Einstein.
Yeah, I think that's my recollection. That for the Einstein perihelion shift, you don't need the spin of Mercury.
I think that's just because to which order you're computing the. Yeah, because we're always computing the scattering angle. in a post-Newtonian expansion.
I see.
Excuse me,
Yeah, go ahead.
About, may I ask?
Yes, please.
Yeah, about next two-iconal approximation. I mean, there is some pattern that you can identify. Do you expect something new?
The next
one.
You mean in the economic approximation? Sorry.
Yeah, next two-iconal approximation of the effective potential.
Yeah, we haven't thought about.
You don't have just the three amplitude, but the loops that.
So that's right.
I mean, the question is, they could exponentiate. Which one?
Yeah. So first of all, yes, of course, yes. So indeed, so that's what we're doing right now. So we're doing the next. So in terms of the scattering amplitude, we're considering the second post-Minkowski, so 2 p.m. expansion, where basically the loop comes in, and that will also exponentiate. And so the final, so it'll be cool if this happens. So as I mentioned before, that at the 2 p.m. order, there's this ambiguity associated with the 2 black hole, 2 graviton exchange. This is relevant at the 2 p.m. order for the economic phase computation. And there's various conjecture about what is actually the nice selection or what is the principle to select the correct contact terms for these things. And it'll be nice to see if this contact term, the selection for this contact term, for example, the specific soft rigid behavior, if it's unique in some sense, then it also corresponds to the same minimal entanglement entropy. That'll be something interesting. And actually we're trying. This is what we're trying to do. So we're trying to compare different principles acting at the 2 p.m. level on the economic phase.
Okay, thanks.
Sorry, just again a basic question. So here, when you do the loops, the divergence doesn't come in because only zero momentum runs, which is what is relevant for the.
When you consider loops, at least at this level, because we're talking about the long range effect. So, for example, if we just talk about ordinary quantum field theory, then what is relevant for the classical effect at one loop is actually the triangle, which you know that the triangle, for example, the triangle scalar diagram doesn't have any UV divergence.
Right.
So that's what is relevant for the classical piece. We're not talking, we're not considering the full quantum, of course,
Newton, I wanted to ask, through this talk, have you gone past 1 p.m. and 2 p.m. in Taiwan time?
Very nice. Yes, it's beyond 2 p.m. Yes.
Okay, any more questions?
Hello. So this is somewhat of a slightly tangential question, but these various, for example, this idea of looking at S matrix and converting it into effective potential and so on.
Yes.
Do you know whether the analogs of that can be done in ADS for things moving in ADS instead of in flat space?
But what would be the EFT in the ADS space that one is thinking about?
What would be the, sorry?
What is what would be the observable that one will be interested in ADS space? So for example, yes.
For example, let's say I want to compute the binding energy. This is kind of related by ADS CFT to the anomalous dimensions of operators and so on the CFT side. let's say that's a physical problem I want to answer, and I want to like, somehow relate it to some TFT correlation functions or something.
But I would imagine that in ADS space, I mean here there's a so in this I think there's here there's a competition. So in the traditional GR computation is a PN because they're doing non-relativistic, and the amplitude way of doing things is completely relativistic, and in a completely on-shell fashion. But I think so then there's a that's why we could say something that the usual non-relativistic approach, I mean, or the setup is drastically different. But in ADS, I would imagine that any observable that you're interested in is you still respect the full symmetry, right? So it's not in terms of traditionally there's a non-relativistic computation in which then you want to do it in a relativistic way.
Yeah,
sorry,
that I agree with.
Loga, can your question be taken as is it about asking about iconization in ADS?
So you can try to calculate it via equivalent approximation, but I was asking, there are various kinds of questions which can be asked. All of them are interesting, but I was asking a very specific question, which is that whether there is a so here there is a in flat space there is a way of kind of characterizing things on shell or things in some invariant way. Without getting into issues about gauge invariance and all that stuff. Yes. Where you relate what is happening at the level of S matrix and what is happening at the level of, let's say, effective potential or something or something like that. Now, one can ask whether there's a similar statement in ADS CFT where, you can talk about CFT correlation functions on one hand and what is happening about anomalous dimensions. Okay, on the other hand, and whether whether there's a direct link that can be given between them in the same vein.
I think there is, right? I mean, for instance, at least leading order shifts of double trace anomalous dimensions just come from the Newtonian potential.
Yes, there is. But I was asking whether there is an effective way of computing them. This is really a question of effectiveness. Yes, there is.
Yeah. The previous talk in this series by BC was also concerned with these issues, right? I don't know whether you attended it, but there also she talked about how to fix the anomalous, the loop diagrams in the bulk and how what is it that they're actually measuring. So this seems kind of related to your question.
Yeah, I'm sorry, I was not there for BC's talk. Yeah. So,
yeah. Maybe relatedly, I could ask you this idea of this effective potential. Does it break down at some order, at the order at which radiation, does the effective potential become very non-local at some order?
Yeah. So there's, of course, this is really only computing the conservative part, and there's also the radiation effect that, indeed, that kicks in at a certain PN order. That's the radiation effect also becomes important. Yes.
And then after that order, to talk about an effective potential becomes increasingly unnatural because it would be highly non-local effective potential.
Yeah, I think so. Yeah, but but I think it's pretty. Yeah, sorry, I don't have exactly which PN order that starts to kick in.
That's fine. But it seems to me, Loga, that everything you could do in flat space, you could do in ADS space to the same order. If radiation is not important, everything will be in some sense some effective potential.
Yeah, but once the radiation is important, you can do it with Schwinger-Kalish. But okay, but that's a different.
Once radiation is important, please say that again.
You can do it with Schwinger-Kalish because it becomes a dissipative system.
You can do Schwinger-Kalish, but it's going to become effective. Oh no, but there's going to be some effective non-locality. Right, what you feel at some later time will depend on what was happening at an earlier time in some irreducible way.
Okay, it depends on. Okay, this is a different question. If you assume that the radiation is just flying off, right? There is no. I mean, there's a sense in which you can just ask, like what we write for, like radiation reaction force, right? We can write on effective dissipative force, but yeah.
No, but I was talking about the fact that when at some early time the thing accelerated, produced a radiation field, and things will then react to that radiation field at later times.
Sure.
It's intrinsically non-local.
Yes, sure. Like yeah, then it's a question of the system and so on and so forth, and what is the radiation and how much is the back reaction. But
this happens at some order. Up to that order, everything will be great. After that will be more and more. I mean, you could call it a potential, but become, to my taste, increasingly unnatural to call it.
That's okay. Yeah, I agree with that. Yeah.
Yutin,
yes.
Can these techniques be applied to compute applied to this gravitational waves from a merger?
You mean are these computations relevant for the gravitational wave?
Not perhaps these, but just these techniques, these on-shell techniques.
Yeah, I mean, well, so of course for the gravitational wave, as I mentioned in the in-spiral phase, so there what they want is of course depends on which order you're computing things, and of course you need to have the conservative potential, and the conservative potential which gives you the equations of motions for these binary systems. So yes, so these are relevant for the so for example, as I mentioned, as I mentioned here, where the gravitational are already computing these spin-dependent pieces, and for example, at 1 p.m. to particular order, and these, I mean, of course, the really question is if they care to that, or because spin effects are not that easy to see.
What effects?
The spin effects. These are not that easy to actually measure, but as of course, as they are interested in higher order, then these, for example, here we already give the all order results. And these references are what has been computed in the community so far. So
and nothing at 2 p.m.
And 2 p.m. is relevant. Yeah. So there's also 2 p.m. computations, and yes, and this of course can be also used at 2 p.m. Yeah. So in terms of computing these conservative part of the potential, yes, this is relevant, and which actually many people are doing at this moment. And some are still using Lagrangian Lagrangian methods to do this, and some, like for us, we're doing it completely on-shell way.
Okay, thank you.
Yeah, but as Shiraz mentioned, at particular order, the radiation effect starts to kick in, and then there's another set of computations that needs to be done there.
Any more questions? Okay, if not, let's thank Yutin again for a very nice talk.
Okay, thank you very much. Thanks a lot, really, for the good questions.
Yutin, I thought it was a fantastic. Really, I mean, I hadn't followed this stuff. It's just very informative and was very interesting. Thank you very much.
Well, thanks, Shiraz. Thank you. Yeah, hopefully, I can visit you guys soon.
Yeah, we would love that.
I hope we can have you visit us at some point when all this goes away.
All right. Okay. Thank you, Yutin. Thank you. Thanks again. Bye-bye.
Take care. Bye.
Bye.